The student's two-sample unpaired t-test is what we will use to compare the means of two different samples representing two different populations. The name comes from a pen name of the guy that developed this in the 1920s. And this is an unpaired t-test because one data set on one population does not necessarily correlate with another data set on the other population. This allows us to say with a 95% confidence that the difference between the two sample means is a real difference and not just due to chance or sampling error. The other way we'll say this is there is less than 5% chance that the difference that we'd see is due to random chance or sampling error. So our hypotheses that we will state for the statistical test is different than a scientific hypothesis that's much more generalized. This is just a statistical hypothesis, and we have two. One is referred to as the null hypothesis, and the term null, like null and void, is basically means zero or nothing. If you nullify a marriage, it's like it never happened. So the null hypothesis, basically, it will be rejected if the probability that the difference that we see between the two means of the two samples is less than 5%, if that probability occurred by chance. Okay, if the null hypothesis is rejected, then there is a significant difference between the two means of those two samples. So we have the by default, if the null hypothesis is rejected, we will accept the alternative hypothesis. The null hypothesis, which you see the symbol as H sub 0, states that there is no difference between the means of the two populations, of the two samples representing the two different populations. So the mean of population 1 would equal the mean of population 2. Now, if that is rejected, then we go with the alternative hypothesis, which simply states that there is a difference between the mean and of the two samples representing two different populations. So the mean of population 1 would not equal the mean of population 2. We're not saying anything about which mean is greater or lesser. We're just saying whether the means are equal or the means are not equal. So stating the hypothesis for this data set, which is the dataset salamander PDF that's available on Canvas. We're looking at two different populations of salamanders, and we're measuring the snout vent length. So the number that you see is the SVL, the distance between the tip of the nose and the vent, which is the cloaca kind of structure where the urinary and digestive systems leave the animal. So, a simple statement of the null hypothesis is that there is no difference between the snout vent length between the two different populations, and the alternative hypothesis says there is a difference in the snout vent length between the two populations. If you notice those two statements, there is only one word difference. There is no difference versus there is a difference. So when do we know when to reject or accept the null hypothesis? And by default, we're always starting with the null hypothesis. It's kind of thought that in science you can never prove something is true. You can only prove that something is untrue. So we're going to calculate a t-value, and the t-value, if it's greater than a critical value, the null hypothesis is rejected. The critical value is a value that you can find on a table that's easily Googleable. There is a table in your laboratory manual. But basically, those numbers vary depending on the type of depending on the type of statistical test that you actually do. There are various types of t-tests out there. So if the t-value is greater than a critical value, it tells you that the difference between the population means being due to chance is less than 5%, and so then that difference is significant. Therefore, if the t-value is greater than the critical value, the null hypothesis that there is no difference is rejected. And then by default, the alternative hypothesis stating that there is a difference between the two means is accepted. That's if your t-value is larger than your critical value. So when the t-value is less than the critical value, we accept the null hypothesis. That would indicate that the probability of the difference that we see in the means between the two populations being solely due to chance or variance is greater than 5%, and that is more than we're willing to accept. Basically, we want to be sure that we are 95% sure or only have a 5% or less chance of being wrong, which is what that 5% basically tells us. So if the t-value is less than the critical value, the difference is not significant. Therefore, the null hypothesis stating that there's no difference between the sample means is accepted. So if we accept the null hypothesis, then by default we reject the alternative hypothesis. Those two are mutually exclusive, basically. So the symbols used in statistics, if you notice the column on the left, the first three things relate to the population: mean, variance, and standard deviation. The column on the right is a sample: mean, variance, and standard deviation. We're looking at a sample of a population, so we're going to be using what they refer to as X bar, the X with a line over top of it, the sample variation, and the deviation, which you notice the deviation is S and the variance is S squared. Now remember the relationship to two: the variance is the square of the deviation, and the deviation is the square root of the variance, which is why they use the same symbol, but the variance is the squared symbol. Degrees of freedom is, again, your sample size minus 1, and alpha is the p-level, or the probability level we're going to use for our test, which is 5%. That's the probability that we could be wrong. We could be seeing the difference between those two populations is strictly chance. So your calculation for finding the t-value you see there, and we'll go over a little more on the next slide. So the t-value, it may look daunting, but really we've got everything that we need, or we'll calculate everything we need to plug in this equation. We need the mean for each sample, which you see the mean for sample 1 is x bar 1 minus the mean for sample 2 is x bar 2, and these vertical lines on either side, they're telling you it's the absolute value. It doesn't matter whether they end up negative or positive. You're going to square them, and even if you multiply them negative by a negative, you still get a positive. So it doesn't matter whether they're negative or positive. The variance for each sample, here is the variance for population 1, variance for population 2. We will calculate both of those. The size, the n value for each one, the size of the sample, we know that. And eventually we'll need the degrees of freedom. But how you get the variance is what they refer to as the sum of the squares divided by the degrees of freedom, n minus 1. And the sum of the squares we'll calculate. Part of the assignment, for those of you who did not attend the Zoom meeting, there is an assignment on Canvas where I want you to work all this out by hand, so you can appreciate what all is done by the computers and calculators that we have today. Okay, so step one, you calculate the mean for each population, and again, it's this X bar. So you're going to calculate the mean for the intermittent stream. You're going to add all these numbers up and divide by the population size, which is 11 for this population, and you should get 38.64. For the permanent stream, you're going to add all these up and divide by, I believe it's 16, and get 41 as the mean. So that's a start. That's how we get the mean for each population. Now we're going to calculate the variance for each population. We're going to basically square the difference between the mean and each value, sum these numbers, and then divide by the degrees of freedom. This is the sum of the squares, and we're going to divide by the degrees of freedom to get the variance for each population. Okay, so for the intermittent stream, I just kind of plug this into a simple spreadsheet. So we're going to add up all these numbers. We get 425. That is the sum of all of our numbers, and find the mean. We divide 425 by n, by 11. We should get 38.6. Now, that is our mean. So for the next column, we're going to take the difference between each of these numbers and the mean. So 40 minus 38.63 gives us 1.36. 39 minus 38.6 gives us 0.36. 38 minus 38.6 gives us 0.6. And again, it doesn't matter whether negative or positive, whether you subtract one from the other, because eventually we're going to square all these numbers. Okay, and then the largest is our 45 minus our mean is 6.36. So then we take all the numbers in this category, square them. All right, so 1.3636 times 1.3636 is 1.8595. We're going to do this for each individual number, square each of these numbers. Then we're going to sum up this column of squares and get what's referred to as our sum of squares. So this category is 56.5, and we divide our sum of squares by the degrees of freedom, which is one less than our sample size. So this divided by 10 is 5.6. That gives us our sample variance. Now you can take the square of that and get the standard deviation, although honestly in this calculation we don't need our standard deviation. All we need is our variance. But if you were talking about standard deviations, that's how you would calculate that. Same thing in the permanent stream population. You add up all of our values, get 656. Divide that by the sample size divided by 16, and you get a mean of 41. So this is relatively a little bit easier. We've got a mean as an integer number. So the difference between our each value and our mean is this column. Then you take this column and square that, and then you sum up the squares for the sum of squares. That was 108. Divide that by our degrees of freedom at 15, and you get 7.2. That's our sample variance. Again, you can take the square root of that and get the standard deviation, but for this calculation, all we need is the standard or the sample variance. So you should be able to complete this table with everything we just calculated. You've got the sample size for each sample. You have the mean for each sample. You also have the sample variance for each sample, which is what we just calculated, and the degrees of freedom. Okay, remember that's one less than the sample size. So completing this table will set you up for completing this calculation. So we have the two means. All right, 38.6 minus 41. We have the sample variance. We have the sample size. So for our first population is 5.6 divided by 11, 7.2 divided by 16. Now remember, these are in parentheses. You do the division first, then you add up the numbers. So 5.6 divided by 11 gives us 0.514. 7.2 divided by 16 gives us 0.45. And again, we're doing the absolute value for this number here. It doesn't matter whether it's negative or positive, but you end up with 2.36 divided by 0.9818. And again, you add these up, then you would take the square of those numbers, the square root of those numbers, and that gives you a t-value of 2.403. Okay, that is the t-value. So we we only get one t-value. That is a number that allows us to compare one population for the other. Remember, with each population, you're going to get a mean, a sample, sample size, sample variance, and degrees of freedom for each population. But when we talk about a t-value, we only have one t-value. That is one number for both populations. So you can find a critical value chart anywhere on the internet. Just make sure you're searching for unpaired t-test if you look for it for ours. There are different critical value charts out there for different statistical tests, so just make sure you're looking for the right test. But if you notice, the critical value as the degrees of freedom increases, the critical value number decreases. And the degrees of freedom we use is a total degrees of freedom between our two sample size. So we had a degree of freedom of 10 for one for our first population, and a degree of freedom of 15 for our second population. So that actually is not on this chart. I guess in years past in GenBio, they've used other data sets where there is 20 or less total degrees of freedom, which would be 22 or less total samples between the two populations. But regardless, ours is 2.4, so we fall into right here. Even if we only had 7 degrees of freedom, we could still say our t-value is greater than a critical value. So even at 20, if you notice, it's even lower. So at this point, we would say our t-value is greater than our critical value, and we will then reject the null hypothesis. So our t-value in this case again is above our critical value at degrees of freedom of 25. So we will reject the null hypothesis, stating there is no difference between the populations, and accept the alternative hypothesis. So our statement of conclusion, we basically just state simply what we see. The salamanders from the permanent stream with a mean of 41 were larger than salamanders from the intermittent stream with a mean of 38.6. And also with the concluding statement, you want to add, not only have both means, but you want to give the t-value that you had and the probability of less than 5%. Both of those should be stated with that final concluding statement of your findings. So this page again is is available as a PDF on Canvas, and there is an assignment on there. I think it's due by next Monday after your class, but I want you guys to basically go through this and work through these by hand, and I want to see the answers you guys have to these questions. I want to make sure you guys come up with the same math that I did, and just kind of work them all by hand. So you've got the mean standard deviation for each sample, the answer to the appropriate statistical test. Number 2 is the t-test. We're not going over any other tests at this moment, with being online and all that. Statements of the null and alternative hypothesis. You've got examples of both of those within this PowerPoint. And the value of the statistical test, the t-value, degrees of freedom, and of course the probability level is going to be less than 5% or 0.05. And state your conclusion, indicate which hypothesis you rejected or accepted. All right, so that basically can be found on Canvas as an assignment, and again, this last page is also a PDF that's on Canvas as well. good luck with that, and don't hesitate again to email me or contact me in some way, and we'll get together and answer your questions. All right. Thank you.